All right, so to wrap up today, the START rule, right? So the essential parts of the STAR rule, make sure that we tokenize everything. It never fails, right? We never get any result from this. We should be able to tokenize even if it's an empty string, okay? Then of course, we do the heavy stuff in that expression rule, which deals with challenges such as understanding individual tokens, making decision of what grammar rules to call and apply, and of course, watching out for errors, right? Because there could be all kinds of errors, and we report them over here, right? So this is where we report the errors. And then if everything else, your homework will be to actually take this top-level node result and go into that tree and do the computation, right? Just actually compute 1 + 2 - 1 and so forth, right? So, but before we do that, right now we have the print method, okay? So the print method, actually, as you know, it basically dumps the tree. Basically, instead of printing the result of an arithmetic expression, the payload of this demo program is that it actually is capable of actually visualizing that abstract syntax tree, which we do create as a result of successful expression rule evaluation, right? Okay, so that's what we need to look at. And as you can see, the result is part of the AST node, right? So the node, which in our case, this result thing that we have is this root node. This is our result. So this result gives us access to the rest of the tree, the rest of its structure, if whatever complexity of it is, right? So print is part of AST node, and it's just one of the methods here. In fact, is the only operation added to my version of AST node. So it says print. So let's take a look. And before we continue, so if we type just a single number like this, or whatever number might be, it's just one number, right? Just one number. In fact, we're also capable of processing fractional numbers like that, right? So they're too interpreted as fractional number. So this is good news because our tokenizer works, our lexer is accepting all of this. In fact, it gets put in the tree and stuff like that. However, if we do use one of the binary operators that we typically use in arithmetic, you can see that the result of it is no longer just the number being printed, because obviously in the case of one number, what happens is that this result node right here, let me just scroll that we can see what's going on. Right? So if we are if we're just entering a single number like this, the result is printed, and I'm trying to make sure that everything is visible. Okay, so this prints a single number because it simply finds that the result, the node type of the result is a number, and it says, there is no tree to print. There's nothing fancy to print. It just basically prints the number and says success on the next line over here, and we proceed back to the prompt, right? However, if we do have a tree, this is where we enter, and right now we're looking at the print method of this as an example right now. We're looking at this top level node. All right, so let's actually use some blank space here so that if we need to illustrate this, we can, we've been through so many different iterations of this already that it's getting crowded in here, right? So our situation is, as an example, 1 + 2, right? And we know that the tree that gets constructed is this plus, okay, and then 1, supposedly, and then 2, supposedly, right? And these are also the same type of node. So these 1 and 2 nodes with numerical type, they too have the left-hand side and the right-hand side, but we don't use it, right? We just basically ignore. They both are set to null, right? So they're basically set to null reference, and there are no objects attached there. So, but that's the actual structure which does exist there. So we know that from our implementation, right? So we come in here to look at this thing from the result, right? So the result is basically this root node of the tree, and of course it has this print method right here, right? So the method is print. Okay. So what I do here, I specify the level and I start with 0. If you look at my call to print, I just say print everything at 0 level, and this level is simply an indentation. And I show indentation by dots. For example, if level is not 0, I just simply run this for loop, which basically says system print dot, right? And so I just kind of print a number of dots in a loop depending what the level is, right? So I just I would like to print with indentation. How I do that? Each print method gets a level of indentation, and I, instead of printing spaces, I like to because remember, this is primarily for debugging reason, so I would like to count my my levels and everything. So I like to use a dot, which I can point exactly and know what the level we're talking about. Okay. So as we print this node, which in our case is the plus node, right? 1 plus 2 result should be this. So we need to, so what it does, it prints plus, right? Because again, if we go to this output and if we go to the example of this, you can see that the first thing that gets printed is the plus thing, right? And the plus, of course, is the fact that this node contains the value which is set to a plus, and it just basically prints this plus, because this print method what it has, again, let me resize that everything is visible on our screen, hopefully, right? It basically immediately, this is part of the AST node, right? So the print, after doing some indentation, in my case there is no indentation because level is 0, so none of these dots are printed. So I simply print the value, and this value is getting displayed as plus. Look what happens next. I say if the left hand side isn't null, then we have some other continuation of this tree, right, on this left hand side, right? So you see, I kind of take very disciplined approach that you should not, sometimes it's easy to make a mistake with left and right, so you have to be kind of disciplined with like doing things with respect to the left hand side and the right hand side. Otherwise things can get mixed, you know, in the not very good ways and surprise you this way, right? So we proceed to the left hand side, and we say that if the left hand side node, which is this guy compared to the root node, right, if it's not null, so there is an object there, right? So what I do, I simply say, hey, left hand side print, and I call the same method print again recursively, because that's the only pretty much approach right now, is to, instead of some kind of iterator helper object, essentially shift responsibility to the nodes themselves, and we say, hey, we just printed this plus, now it's time to print anything that this node would like to print. And of course this node will basically have left node and right node set to null. The only thing which it will print is this value, which is 1. And then we're going to go to the right hand side node, which will print 2, and that's exactly what happens. So we print plus, then this is the left-hand side right here. This is the left-hand side. This is the right-hand side. And of course, these two we want to print with the node. And what I do simply is that every time I go to my left side or the right side, I increment the level by 1, right? So 0, the initial 0 level becomes 1, and this is why 1 and 2 are printed with a single dot, right? So if we increase the the sub levels by, let me give it a try, right? If I say 1 minus 2 plus 5, something like that, right? So the parentheses are important. So we try something like that. Of course, this internal expression inside the parentheses, also very commonly referred to as a sub-expression, right? So you should get a sense that this is really just an expression as the rest of the expression, but it's treated as a separate unit inside parentheses, right? So what it does, it just has the plus right there, and the plus operates on 2 and 5, and of course the plus itself already starts at level 1, so therefore it's left and right gets printed at the next level. And then of course over here we could say let me just retype this one. By the way, I can use spaces if I want. Remember, spaces are harmless because they're all skipped. 1 minus 2 plus say 5 minus 6, something like that, right? So we have more nested levels. There you go. Now we went on to use even more nested levels, and now we have more than one dot as a result of basically you can see that the tree is indeed constructed with respect to the required rules, right? So essentially we sort of almost like just rewrite this input with this version of input, right? We could have asked the user to enter this input in order to do the computation, and they would hate us, right? Because they're much more used to something like this, rather than asking people to input something like that, which would be sort of like a prefix notation rather than infix notation such as this, right? So when binary operators are used between the operands, we refer to this as infix notation, right? As opposed to prefix, which would be an operator in front, or postfix, which would be using a notation that uses an operator at the end of the two operands, right? So nevertheless, you can see that you should convince yourself that you can be comfortable about the idea of this print method, right? There's only one instance of print method, but it behaves very differently, right? It's actually always behaves the same way for any node when it just basically prints the value with some indentation as it needs to. But then it says, I'm not going to stop there. If there's anything on the left, which is not null, or on the right, and both for the same for the same token, right? It's just gonna say, I will ask the left-hand side to print itself and the right-hand side to print itself, and that's where we get those nested levels, which basically try to visualize our current tree and hope for. And I actually used this while debugging this application. It took me about 3 iterations to come up with this demo. The first iteration was using stacks instead of nodes, which worked with very simple expressions, but then I tried to mix stacks with trees, which only complicated things, and I got rid of stacks, and I just decided to go with this AST node that we're looking today at in its current version. And in fact, you know, for the sake of ultimate simplicity, I even made the type value in left and right basically public data members, just to reduce as much as possible the code. Of course, this is just a compromise to make demo as affordable as possible. So, but this print method basically highlights, I think ultimately you can say that the nature of print is very similar to the nature of our grammar rules. Grammar rules wanted to call themselves, if they had to, like indirectly, the primary rule wanted to call expression, but of course we know that every expression would go down to call back into the primary. So that's basically an indirect level of recursive calls, whereas this direct attempt to call things recursively, but eventually at some point the left and right nodes will be null, so we will be just basically returning from all of our print calls, and we'll be done with printing the content of that tree. So this thing concludes our discussion. I would encourage you today, at least today, right? So next week I will try to revisit this, but I would strongly encourage you to reread the handout, right? So it comes with a handout, and then of course go to so it basically reinforces our discussion, and then find out what you need to do, because this is what I would like to talk about next week. So till next week, done for today. Thank you very much.